Hi, everyone. My name is Del Jackson. I'm the Senior Product Manager here at Unchained Labs. I'm going to be your moderator for today's session. I just want to say thanks for taking time out of your busy schedule and joining us today. We are going to have a Q&A session at the end of the presentation. To ask questions, you should see a little Q&A button in the Zoom navigation bar. It's going to be either at the bottom or the top of your screen. And from there, you can type your questions at any point during the presentation. We are going to cover them at the end. And if you could, when you submit those questions, don't click the anonymous button. That way, in case we run out of time during the Q&A session, we'll be able to follow up with you afterward to get you an answer. We are going to try to get to as many of them as possible, though. And it's my privilege this morning to introduce Rick Sidler. He's our Director of Field Automation Scientists here at Unchained Labs. With over 20 years of automated chemistry experience, I'm definitely looking forward to hearing Rick walk us through how the OSR can help with the development and optimization of your reaction conditions, particularly for those challenging pressure reactions you might need to do. And so without further delay, I'll hand it over to Rick. How are you today, Rick?
I'm doing great. Thanks, Del. Sorry, I'm just trying to get my screen shared.
No problem. Take it away, sir. Thank you.
Thank you. Can you see the slides okay?
Yes.
Okay, great. Thanks. Welcome, everyone. Glad you could join us today. I don't know where all of you are joining us from, but I know here in the Northeast, it's been a long, cold, gray winter here. But last week we had our first day above 50 degrees Fahrenheit with a nice sunny blue sky, sure sign that spring is on the way. While I was outside enjoying a few minutes of the good weather, I got to daydreaming about the first cookout of spring for my grill. And, you know, I was trying to debate some of the variables. Should I throw on the old standby burgers and dogs on the grill, or maybe grill some portobello mushrooms, or some chicken marinated in some homemade cayenne pepper sauce? You know, there's a lot of variables, a lot of things to think about. And that got me thinking about you and why you show up to work every day. What you do is incredibly important. It has a huge impact on our daily lives, from discovering and developing new medicines that improve and prolong our life, to developing new materials that give us better batteries, or improve the tires on our cars and bicycles, or improve the performance of our rain jackets, shoes, and fishing gear, our fitness gear. It's all about evaluating variables in your reaction space to achieve the best results. You need to run smart experiments that answer critical questions and quickly get reliable data for making decisions. And you need to do it fast. You need to choose from an endless supply of options or variables for your reaction conditions, different solvents, ligands, catalysts, temperatures, and then quickly narrow that down to the best performing optimization results. That's oftentimes best described by sort of this R&D funnel picture, where you starting out, often need to evaluate hundreds or thousands of discrete variables to see what classes work best for a given transformation. Oftentimes, this is done best on very small scale reactions, microliter size or hundreds of microliters in scale and size. Then you take those promising leads and scale them up to get additional information about the best process conditions, assess safety concerns, and evaluate product properties and performance. Oftentimes, this takes a little bit larger scale because you have additional analyses that you need to do. And this is where the OSR, the Optimization Sampling Reactor, really shines. But the ultimate goal of these is usually to take those very best reaction conditions forward into a kilo lab or a pilot plant or a factory. And in order to do this, you need data. You need data that's fast, that's reproducible, and primarily it's data from a method that you have easy access to and that you can trust. When it comes to pressure reactions, there's a good chance that you just don't have the ability to run reactions on an appropriate scale with the right number of parallel experiments and have the ability to track real-time progress while taking samples for your proven LC or GC techniques. These things that allow you to track low-level impurity formation and look at things like the diastereoselectivity or the enantioselectivity and how those may change over time. Whether you're looking for real-time gas uptake monitoring that allows you to follow the progress of the reaction, with data that can be exported for kinetics analysis, or time point samples for UPLC or GC analysis. The ability to create plots of reaction profiles where you can see starting materials disappear, products form, and maybe intermediates come in over the course of the reaction. And also allow you to track the things like the fate and purge of byproducts in the reactions. You really want or need the ability to collect as little or as much data as you need. And ultimately, in the end, you want that data to be centralized and searchable so you can use it in future studies. Whether you're running a new molecule or a new campaign, or whether you're embarking into a trek into the machine learning and artificial intelligence area. For pressure reactions, it really doesn't get any better than the OSR. The OSR is a module of 8 individual reactors. The reactors have individual temperature and pressure control, can run anywhere from -15 degrees C up to 200 degrees C. We can run reactions up to 400 PSI with the option for increasing that to 750 PSI range. And it covers a wide range of reaction volumes, anywhere from about 0.6 milliliters all the way up to a 25 milliliter working volume. Importantly, the reactions have overhead stirring and the ability to sample, to take samples into or out of the reactions during the course of the reaction without interrupting the pressure of the reaction environment. The wide range of working volumes is accomplished by having a couple of different reactor sizes. We have shown on the left the standard OSR reaction vials that we use for running 4 milliliter to 8 milliliter reactions. On the right-hand side, you'll see low volume inserts. We have a stainless steel insert that can fill the bulk of the reactor and can hold in a smaller glass insert tube inside that. That allows us to run reactions from about 0.6 milliliters to 4 milliliters in volume. You'll notice the stir shafts are hollow and they have a cutout center, and that's what allows us to take a sampling needle down into the reactor vessels to add materials or to remove samples during the course of the reaction. This OSR module can be placed on one of our robotics platforms. We have 2 robotics platforms, the Junior, which is our smaller platform, primarily more for focused workflows and workflow applications, or on our big Kahuna system, our sort of flagship that allows us to do more end-to-end automated workflows. We can customize the layouts of these decks from a collection of standard deck and arm element modules. We kind of think of them as Lego bricks of building our systems, so we can mix and match those to build whatever system you need for your specific workflows. An example configuration for a Junior with an optimization sampling reactor might look something like this, where we have shown here on the left-hand side of the robot, the optimization sampling reactor itself. Next to that, we're seeing a vortexing station with 3 microtiter plate format positions. Then moving over to the right from there, we have a heated, cooled, magnetically stirred bay and a passive rack bay. These allow us to do things like preparing reagents or catalysts that are going to be added into the OSR reactions. Or when we're pulling samples out, we can put them in plates or vials where we can quench those reactions and do further processing before they're ready for their analytic techniques or analyses. We can also use these deck positions for other types of chemistry and scales of chemistry. You'll notice looking at the picture here, we work in microtiter plate formats, and sort of any size vial arrays that fit into those formats we can utilize on the system. Well, the OSR is mainly used by a lot of people for pressurized reactions. We also have a lot of customers using the OSR for other types of work as well. Things as diverse as ADC conjugation reactions, for non-pressure chemistry, for example, for cross-coupling reactions with the excellent temperature control and the overhead stirring, the ability to efficiently mix heterogeneous mixtures of materials. A number of researchers using it to study crystallization and crystallization processes, and many others. You can configure a junior platform system with a single OSR module. You can configure a junior with up to 3 of those modules. You can actually put up to 6 OSR modules on a single big Kahuna chassis, as you see here in the bottom picture. That really allows you to have a lot of diversity for larger scale development needs. The OSR is the one key tool that really allows you to cover the breadth of your research needs, everything from discovering new catalysts or conditions to screening for discrete variables in your reaction space, taking those best yields and optimizing continuous variables, for example. Everything you need to discover and build process knowledge and to develop a robust process can be done on the OSR reactor. Up till now, we've talked mostly about the hardware of the OSR piece, but we do have the software component, LIA, which is our lab execution and analysis software, which really brings it all together and supports the entire research process. The first component of the LIA software is Library Studio. This allows for simple drag and drop to create library designs, mixtures of things that you want in your experiments. And you can define temperature and pressure and other reaction variables there. The Library Studio design is then read into a program called Automation Studio, which is responsible for controlling the robot and making it do the procedure that you set out in the Library Studio design. You do not need to program the robot per se. The programming comes from the Library Studio design that you created. In addition to controlling our robot platforms, Automation Studio can also control third-party instruments that are under its domain or its control. And all of the analytic data and processing data that comes back out of the robotic system and any integrated analytics can then be stored in a central database where it can be viewed and reported. We can use tools such as Polyview or LIA analysis to query and view and report that data in a way to allow you to drive decision-making. We can also support data to statistical packages and data viewing packages like JMP or Excel. Because each of these software packages is separate, you can separate out the experimental design from the running of the experiments, from the analysis of the data, and all can be done at separate locations where the expertise might reside within your organization. As we mentioned earlier, all of the data is stored in a centralized location or a database in a structured format. So it's available for you to facilitate your access, viewing, and organization of the data. And increasingly, we're finding people are really happy with the ability to access that for machine learning and artificial intelligence applications. The Automation Studio software has an intuitive UI, which gives you access to all the information that you need. Shown here, you're seeing the robot deck layout for that 6-module OSR system, shown here. So you can see the temperatures, the pressures, and all of the information that you need, all at your fingertips. You can view real-time live updates of temperature, pressure, gas uptake during the course of the reaction. All of this data gets stored into the database. You can then view reports, which can include everything from contextual information about the composition of your experiments, the catalysts, the ligands, the solvents, the amounts of each of those materials, alongside graphical information shown here, for example, the HPLC chromatograms, along with retention times of the various peaks in each chromatogram and their area percents. This, of course, is not limited just to the OSR, the Optimization Sampling Reactor. We also have a whole suite of tools that help in the preparation, processing, and analysis of your reaction conditions. Such things as solid and liquid dispensing, all the way through screw capping and decapping and labeling of containers. In the processing space, most commonly it's around heating, cooling, mixing, doing electrochemistry or photochemistry. And in addition to a variety of different pressure reaction conditions, the OSR being one of them. And then even workup of your reactions once they've been completed using techniques such as solid phase extraction, liquid-liquid extraction, and evaporation. And finally, because we're running reactions to get information, we want to do some sort of analysis. This can be real-time gas uptake monitoring. It can be pH measurement. It could be through vial Raman measurement, where we can follow the course of the reaction by Raman spectroscopy. We also integrate with a lot of third-party devices like HPLCs and GCs, for example. And we can even include on-deck injectors and injector ports to facilitate that. We can prepare plates of samples and move those, either automated or manually move those into integrated LC instruments. And to facilitate these analyses, we can do a variety of different sample prep manipulations there, whether it's quenching reactions, diluting them, filtering them, getting them into different solvent systems. In the remaining few minutes we have, let's look at a real-world application of the OSR. And what I want to show is a recent example, a recent publication from the groups at Scripps and BMS. Donna Blackman at Scripps and Michael Schmidt from BMS recently published a paper on the enantioselective hydrogenation of pyridyl substituted alkenes. Basically, it's the reaction that you see here with the blue text. So these substituted pyridyl reactions, hydrogenations of those. This is sort of a secondary screening application. You know general conditions for the reaction that work. You want to see what the effects of making changes to that system are. Well, the first thing that you want to be able to do is have confidence in your method. And so the first real test here is to ensure that the results are reproducible and correlate to product formation, as the authors have demonstrated here. So in this example, they're showing duplicate reactions and showing how closely those track as far as formation of product or product concentration as a function of time. And product concentration is measured by real-time gas uptake. And so it's directly related to the product concentration. Once you're confident in the reaction conditions that you have and that they're reproducible and will give you good results, you can then begin to vary things in your reaction to see the effects of changing those parameters. So here, for example, they're looking at changing the amount of added p-cymene at 3 different levels. Here, so either no additional p-cymene, 1 equivalent, or 2 equivalents. They're running these experiments in duplicate. So there's 6 experiments total. They could all be run in a single OSR run because you have 8 reactors in that system. And again, you're able to distinguish between those. You can see the 2 reactions with no p-cymene added here on the very top. In the center, you actually see 2 overlapping lines for the 1 equivalent of added material, and then moving further down into the right, you see the ones with 2 equivalents of p-cymene. So you can see we're able to, in the OSR from gas uptake, distinguish between reaction conditions here, and you can see the reproducibility of those from the replicate samples. You can then move on to looking at other variables in your reaction space. So for example, we could look at the effect of changing substituents on the 3 position of the pyridyl ring. So again, here are 8 different substituents on those rings, 8 different reactions. They could all be run in a single OSR reaction or a single OSR run. And you can see here from uptake a wide variety of different reactivities based on those different 3 substituents. Due to the scale of the OSR, you can choose how you want to run these. You could run these on a very small scale to minimize the amount of material required for your study. You could run them on an intermediate scale that gives you enough product for further analysis, whether that's looking at HPLC, SFC, crystallizing those materials and looking at isolation and purification. Or you could even make enough material from each one of these individual runs to move those materials forward into a telescoped library synthesis array. Well, I hope that we have whetted your appetite for the OSR. If so, please reach out to us. We'd love to continue the conversation around how we could help with your variables. And at that point, Del, I think I'll turn it back to you in case there are questions that have come in.
All right. I think yeah. Thank you, Rick. I really enjoyed that. I always like listening to you talk. I especially like the points you made about how important it is to be smart and fast in our research today and the role that the OSR can play with that. play in that, allowing you to run multiple experiments in parallel and get that real-time gas uptake data. So enough about what I got out of the presentation, though. Let's hear from the people who attended. And thankfully, we have a good amount of questions. So I'll just start firing them off to you. I'll grill you a little bit to
All
keep
right.
it so the first question we have is, what gases, someone asked, can they use with the OSR?
Most commonly, people are using things like hydrogen or carbon monoxide in small molecular research world. We have a number of customers using the OSR system for polymerization research, and they're typically using things like ethylene or propylene, among other gases. We have had people use it for oxidation studies and other techniques as well. So a wide variety of gases can be used.
Yeah, that's good to know. Someone also asked, can they take multiple samples over the reaction time? And if so, how many and how fast?
Yeah, a really cool feature of this is it's very easy to program when you want to take samples from the mixtures. You can take multiple samples. You can take them at different time points over the course of the reaction. It takes approximately 2 to 3 minutes per sample to get into the pressurized reactor, pull the sample and get back out of the reactor, deposit your sample into a collection container, and then wash the needle. So turnaround time from sample to sample is somewhere in the ballpark of around 3 minutes. It depends a little bit on the pressure that you're running at.
Still seems fairly fast. And this question, I hope I get it right. They asked about the big kahuna. Can you weigh into the OSR tubes on the big kahuna? Is that possible?
Yes, you can. You can use a vial plate gripper to pick up tubes, place them in a balance, dispense solids into those tubes, and move them back. You still need to manually place the tubes inside the OSR and seal the reactor head down because they are under pressure. So they do need to be the torque down to a specified torque.
Okay, great. And I think I heard you mention HPLC integration. So can you integrate the OSR robot with online HPLC injection?
Yes, you can. You can pull samples from the OSR, dilute those into a material, and then you can inject those directly onto an HPLC injection port on the robot deck. Or you can prepare plates of samples and then transfer those entire plates into an LC for further analysis.
Nice, cool. A question, I think this was on one of your slides, but someone asked for a little bit more detail. What's the difference between OSR and then DSPR and SPR? So a lot of alphabet soup, so maybe those mean too.
Yeah, exactly. So the OSR, as you've seen, it's our optimization sampling reactor. It's a little bit larger scale volumes with individual gas pressure, gas pressurization and monitoring, and overhead stirring. The DSPR is a smaller scale plate-based system, so it has a common headspace over all of the reactors. They're generally run on a much smaller scale, so we're running those typically in 1 milliliter vials with a couple of 100 microliters in fill, up to maybe a half a milliliter to a milliliter in volume. Each one of the reactions sees the same pressure, sees the same temperature, and shares a common headspace with those gases, so you don't get individual uptake pressure reactors. The DSPR is really great if you want to screen a whole variety of different catalysts or ligands just to see which classes work. And then once you've identified those classes, then you can go forward with an individual ligands or catalysts or things in the OSR reactors.
Okay, great. How hard is it to switch between reaction sizes on the OSR?
Yeah, that's really easy. You saw the tubes there, the larger tubes for the OSR. You can drop those in, click on a stir paddle that's the appropriate size for that vessel. When you want to go to the smaller tubes, you just drop in that insert reactor, drop in a tube, and click in a different size stir paddle. There's no changes needed to the software or the hardware settings to do that, and you could even run with large tubes and small tubes in one OSR module at the same time.
Oh, cool. Okay, we have a few more questions. Are you still
good?
Through? Okay, great.
I'm good.
So, and then also for our attendees, you can continue to ask them. We'll probably go right up until, for the next few minutes. But the next question is, do we need a specific needle on the arm to sample from the OSR reactions?
Yeah, the OSR reactor has a dedicated arm that you need to use to do that. Because the reactions are still under pressure while you're taking the samples, we do have to have the ability to get in and out of those without disturbing that pressurized atmosphere. So it does require a specialized arm to add samples or take samples out. Once the samples have been removed and placed into a receptacle or container on the robot deck, then you can use other arms to add materials or measure pH or do other things to those.
Okay. And can the OSR be used for other non-pressure reactions?
Yes, absolutely. We have a number of customers who are using it for things like crystallization reactions because of the good overhead stirring and mixing and temperature control. So we can do temperature ramping and profiling. A number of customers who use it for other reactions like cross couplings, where you have heterogeneous mixtures of materials and you want to run there. You can also run non-reactive pressure gas experiments where you, for example, could put a slight positive pressure of nitrogen, an inert gas, on the headspace of the reactors. And then you could run reactions at close to the boiling point without actually refluxing your solvents.
Okay. And then finally, you had mentioned the ability to integrate other devices. Someone asked specifically about Biotage MRV on the Junior platform. Do you have any comments on if we can integrate that?
I don't know about that right off the top of my head. I would need to look into that.
So yeah, in general, and that's a great question. We can follow up individually, but in general, we can always evaluate the compatibility of integrating that, but we have a bunch of flexibility on Big Kahuna and Junior platforms with Automation Studio to incorporate those integrations. All right. Well, thanks, Rick, for letting us pick your brain even a little bit more, and for the presentation. I know I learned a lot. And
thank you. Thanks everyone for joining.
Yeah. And I also want to, yeah, exactly. Thank everyone else who joined us today. And just to go along those lines, if you do want to have further conversations with Rick himself and his amazing mustache, or anybody else on the team, you can get in touch with us at info@unchainedlabs.com, or you can go to our website, which is unchainedlabs.com as well. And we really love to connect with you. You can see we have a bunch of experience here with automated chemistry. And so it's great to have those conversations. Thanks again for attending the seminar. And Rick and I hope you have a great rest of your day. Bye-bye.